Okay guys, in this video we're going to talk about something called vector components, which I'm actually going to come to in a second. But before we do, I want to just revisit something we talked about in the last video, but something I want to add to that discussion, which is that in the last video we were talking only about displacement vectors. And the reason we were doing that is displacement vectors are the easiest to kind of visualize and the most intuitive. You can imagine walking along the line, for instance. But the same vector math, the same work we did with the arrows last time could be used for other types of vectors. For instance, could be used for velocity vectors. And I think it's a little less clear or a little less obvious when you're dealing with velocity vectors rather than displacement vectors. So I just want to go over an example now. So let's imagine, for instance, we have a river here. Here's the river, and we're in a boat, and we're trying to move from this side of the shore, from one side of the shore to the other side of the shore. And so we're pushing, here's our paddles, and we're moving in this direction. And maybe we paddle our boat in this direction like so, with a speed of, I don't know, we could say 4 meters per second. That is to say that we're moving 4 meters per second relative to the water, or compared to the water itself. That's the speed we're moving compared to the water. But since it's a river, maybe the water itself is actually moving. There's a current in the river, so the water itself is moving in this direction at, say, 3 meters per second. This is the water current. And so you can see that if we're moving 4 meters per second relative to the water, but the water is moving itself, then we're going to have a speed here that is in this direction. We're going to move this way due to the velocity of the water itself. And so we might want to figure out, what is this velocity? This is the velocity relative to the shore, to the land. And to do that, it might be clear to you that we can combine our two starting vectors. In other words, we can combine the 4 and the 3, and since they're at right angles, we're going to use the Pythagorean Theorem. So let's do that. The way I might simplify this situation by drawing a diagram like so. I might say I've got 4 up, and I've got 3 to the right, and I've drawn the vectors tip to tail. And now to determine the overall resultant displacement, or velocity rather, this is the resultant, I'm going to use the Pythagorean Theorem. So maybe I'll zoom in on this. So the resultant here, I'll call it, since it's a velocity, maybe I'll call it v. And I'll say v equals the square root of 4 squared plus 3 squared, which is the square root of 25, or 5 meters per second. So that's the speed. And then I can use my sine, cosine, tangent in order to figure out the angle. I'm going to figure out this angle right here, and I can say that this angle, theta, is equal to the arc tangent, or I'll write it this way, the inverse tangent of 3 over 4. And use your calculator to figure out what that is. So that's all just to say that the same stuff we talked about last video can be applied to velocity vectors in addition to the two displacement vectors. In fact, it can be used for any vector. All right, so now I want to spend the bulk of our time here talking about vector components. First of all, the word component, this might not be a familiar word. Component just means a piece or part, a part of a whole. Okay, so parts of something are sometimes called the components of that thing. And so, and you'll see why they're called parts of a whole. So maybe to get us started, let's imagine a real world situation. Let's imagine we're on an escalator. So here's an escalator. The escalator is going to bring us from, say, the first floor of some building up to the second floor. So here's the escalator, and we move along the escalator like so. Here it is. We move up the escalator at a velocity of, let's say, 4 meters per second. And maybe the angle of the escalator here, this angle relative to horizontal, is 30 degrees. So if I move 4 meters per second at an angle of 30 degrees above horizontal, like so, I might ask you, am I moving to the right or am I moving up? And I hope you would tell me that I am moving both to the right and I am moving up. In other words, there is a part or a component of the 4 meters per second. There's a component that is to the right, and there is a component that is up. And so maybe you can see now where we're going. I now have a right triangle here. Here's my right triangle, and I know the hypotenuse, but I don't know the legs of the right triangle. So I'm going to do essentially the opposite of what we did in the previous in the previous example involving the canoe on the river. I'm going to start with the hypotenuse and figure out the legs. And these legs are called the components. And maybe I'll call this the y component since it's vertical. And I'll call this one down here the x component since it's horizontal. So this picture's gotten a little messy. Maybe I'm going to redraw it just to make life a little easier. So I've got my 4 meters per second here, and now I want to figure out how much of that 4 meters per second is in the x direction and how much is in the y direction. And to do that, I'm going to utilize this angle here, which is 30 degrees. So here we go. I'm going to use my sine, cosine, and tangent functions. And first of all, maybe I'll find the x component. So this is the x component, and this is the y component. To find x, I'm looking for the side that's adjacent to the angle, and I know the hypotenuse, so I'm going to use cosine. So I could say cosine of 30 degrees is equal to x over 4, and that means that x equals 4 times the cosine of 30. All right, and now go ahead and use your calculator to figure out what that is. It's going to be like, I don't know, maybe it's 3.6 or something like that, 3.6-ish meters per second. To find the y now, to find the vertical component, if this is the horizontal component down here, 3.6, if I want to know how fast am I moving upward, I'm going to use sine. And I'm going to use sine because y is opposite from the angle of 30 degrees, and I have the hypotenuse again. So I'm going to say sine of 30 equals y over 4. So y equals 4 sine 30, which is 2 meters per second. And so what I've done now is I've taken my starting vector, that 4 meters per second, and I've split it up into pieces. The 2 is the piece of the vector going up, and the 3.6-ish is the piece of the vector moving to the right. These here, again, are the components. And it's often helpful to split vectors into components, and I think actually maybe in the next video we'll see an example of when you might use this. But this is actually something we'll do quite frequently in this course. And I want to introduce just a term that you'll hear me use. This process of splitting vectors into components is sometimes called vector resolution. Splitting a vector into components. A vector into components. So that, if you hear me say vector resolution, or if you read that, it just means to split the vector into components. And in the next video, you'll see an example of how we can use this under certain circumstances.